So today I'm going to be talking about post-critically finite cubic polynomials. This is joint work with Jackie Anderson and Michelle Manas. So let's start with some definitions. We're going to let k be a number field and f be a rational function with coefficients in k. We're going to define the orbit of a point to be the image under iteration of f. So all the forward iterates of f. So here we use the notation Fn to be f composed with itself n times. We often want to classify points based on their behavior under the iteration of f, or based on their orbits. So we say a point alpha is pre-periodic if it loops back to alpha again under the orbit. Right? So if eventually, after some number of iterates, it goes back and hits alpha again. And we say that's periodic of period m if that happens after m steps. We say that alpha is a pre-periodic point if the orbit loops back on itself, but maybe not exactly on that point alpha. So maybe it goes k plus m steps and then loops back to the kth step. And then we say this is pre-periodic of period km. So here k is a tail length and m is the length of the cycle. And in both of the cases where we have a pre-periodic point or a periodic point, we notice that alpha will have a finite orbit. And then finally, we say that alpha is a wandering point if the orbit is not finite, so if it has an infinite orbit. So let's look at an example. Let's consider the map z squared minus 1. Well, under this map, let's look at the point 1. Well, 1 maps to 0, which then maps to negative 1, which then maps back to 0. So here we see that 1 is a pre-periodic point, and 0 and 1 are periodic points. And if we look at another point, let's say 2, well, 2 maps to 3, which maps to 8, which maps to 63, and so on. And we can see that this would be an infinite orbit, so that means that 2 is a wandering point. Well, we often want to discuss maps up to some conjugation. And here we're going to say that two maps are conjugate if they're conjugate via an element of PGL2. And this conjugation preserves a lot of the dynamic properties. So if we have a pre-periodic point of a given period for a map F, then that's going to correspond to a pre-periodic point of the same period for the conjugate maps. So throughout this, we'll be talking about maps up to conjugation. And so when we discuss a conjugacy class, we just mean F and all of its conjugates. We're going to let crit of F be the set of the critical points of F. And we mean this in the traditional sense where these are the places where the derivative vanishes. A map is post-critically finite if every element of the critical set has finite forward orbit. So if every critical point has finite forward orbit, so that means that they are fixed, pre-periodic, periodic, then that map will be post-critically finite. And this is one of the properties that is preserved under conjugation. So if we have a post-critically finite map, then all conjugates of that map are also post-critically finite. So if we want to describe post-critically finite maps, we can describe them up to conjugation. Let's look at an example of a post-critically finite polynomial. Let's consider the polynomial 2z cubed minus 3z squared plus 1/2. The critical points for this polynomial are just 0 and 1. And here we have 0 maps to 1/2, which maps back to 0, and 1 maps to negative 1/2, which is a fixed point. So we see that this map is definitely post-critically finite because the critical points 0 and 1 have finite forward orbit. So post-critically finite polynomials have been studied a lot recently, namely in this paper by Ingram in 2011, where he proves this nice finiteness result about post-critically finite polynomials. So if we have post-critically finite polynomials of degree d with coefficients of bounded algebraic degree, then this is going to be a finite set and it's effectively computable. So a nice application of this by Ingram was looking at cubic polynomials that are in the monic-centered form, which is this form here. So if we're looking at these polynomials that are in this monic-centered form that has coefficients in Q, and we want to know which ones are post-critically finite, then it turns out that the coefficients A and B must be in this finite set here. If we're only looking up to conjugation, then we don't want to have two elements from the same conjugacy class, so we in fact do not need to include this pair here because it's going to be conjugate to this pair. So now we might ask the question, well, are these all of the cubic post-critically finite polynomials with rational coefficients? Let's look at an example. We're going to return to that example that we used before of a post-critically finite map, the 2z cubed minus 3z squared plus 1/2. So we can conjugate it to put it in this monic-centered form, but then we notice that this new polynomial doesn't have coefficients in Q. So when Ingram did that search for all of these post-critically finite polynomials with coefficients in Q that are of this monic-centered form, this polynomial was not captured in that search. So the problem was that the monic-centered form doesn't preserve the field of definition. So if we have a cubic polynomial with coefficients in Q and we conjugate it to this monic-centered form, it doesn't necessarily remain in that base field. So then when you perform a search to find all the post-critically finite polynomials of this form, you in fact miss the ones that did not maintain the field of definition when conjugated to this form. So now this begs the question, well, can we use the same techniques but perhaps a different normal form to find all of the PCF cubic polynomials with coefficients that are rational? And well, yes, we can. We have to expand on the techniques a little bit, but we can use the same ideas and we just need different normal forms. In doing this, we find that there are exactly 15 conjugacy classes of cubic PCF polynomials with rational coefficients. Of these, the 6 here denoted in red were found by Ingram, whereas the others we needed to use a different normal form in order to find the post-critically finite polynomials. So our strategy is as follows. We find the normal forms that respect the field of definition. And in order for a map to be PCF, it must be post-critically bounded in each absolute value. So we can find these Archimedean and p-adic bounds on the coefficients of the maps in each of the normal forms in order for the map to be post-critically bounded. So if the coefficients exceeded these bounds, then the orbit of the critical point would escape to infinity, so that we don't want that to happen. So we can use these bounds in every place in order to create a finite search space of possibly PCF maps. Once we have that finite search space, we can just test each of the map in that search space to see if it is PCF or not. So in this talk today, we'll be mostly discussing the normal forms that we found, as well as the PCF maps that arose from each of those normal forms. And the details for steps 2 and 3 will be presented in the live talk on July 1st. So when we're thinking about cubic polynomials, there are 3 different possibilities. Well, that polynomial could have exactly one critical point, could have 2 distinct critical points, and those critical points could either be rational or live in a quadratic extension of the base field. So we need to treat each of these cases a little bit differently when we're looking for this normal form. The unicritical case is the simplest case. So if we have a degree 3 unicritical polynomial, then it's either going to be conjugate to the pure power map z cubed or a unique polynomial of the form az cubed plus 1, and that's going to preserve the field of definition. And this actually extends to higher degrees as well. So if we have any degree d unicritical polynomial, then it's either conjugate to the pure power map z to the d or a unique polynomial of the form a times z to the d plus 1, and conjugating to that form is going to preserve the field of definition. So we can use this normal form to find all of the PCF maps that are unicritical. So we found that if we have a unicritical polynomial with coefficients in Q, then if we are of even degree, then this map will be PCF exactly for two conjugacy classes. First one is when A is -2 or when A is -1. And if we are working with odd degree, then a polynomial is PCF if and only if A is equal to -1. So this fully describes all PCF polynomials with one critical point when we're working over the rational numbers. So what if we have two critical points? And let's consider the case where these critical points are rational. If we're just working over cubic polynomials, then we can take these two critical points and move them to be at 0 and 1. So we conjugate to move the critical points to 0 and 1, and then we see that we're going to obtain a map of the form a times -2z cubed plus 3z squared plus c, and this maintains the field of definition, so those parameters a and c are going to stay in our base field. So if we're looking over the rational numbers for PCF cubic polynomials that have two rational critical points, then we can just use this as our search space, polynomials of this form here, where a and c are rational points. And this extends to higher degrees as well, using something called a dynamical Belli polynomial. So what we did in the cubic case is you can just move these critical points to 0 and 1, and you can do the same thing if you have any degree d polynomial with two critical points, both rational. And then we're going to use these dynamical Belli polynomials. And a dynamical Belli polynomial of degree d is just a map on projective space with fixed critical points 0 and 1. So if we have, we're going to let B denote a dynamical Belli polynomial of degree d, and these subscripts dk are going to denote the degree as well as the ramification index at 1. So the ramification index at 1 is going to be given by d minus k. And then this map is of this form here, which has integer coefficients. So if we have any bicritical polynomial of degree greater than or equal to 3 with two critical points that lie in the base field, then we can always conjugate to a polynomial of the form a times one of these Belli polynomials plus c, and will remain in that base field. So when we're looking at this cubic case, we can perform this search in the cubic case using these bounds that we have on the coefficients, okay, which will be described in detail in the future. And we get that if we have any cubic bicritical PCF polynomial with rational critical points, then it's going to be conjugate to a polynomial of the form a times -2z cubed plus 3z squared plus c, where the pair a and c is contained in this set here. So now we've covered the unicritical case and the bicritical case when the polynomial has rational critical points. And what's left to discuss is the case where we have a cubic polynomial that has two critical points that are not rational. So in the cubic case, we're going to consider bicritical cubic polynomials with critical points that live in a quadratic extension of our base field. And then we can always conjugate to a polynomial of this form here, and this will preserve the field of definition. Okay, so we will stay in the same field that we were in originally. And here D is just going to be a square-free integer. This extends to higher degrees as well. So we can use this form here. So if we have a map of degree D with a fixed point at 0 and critical points at plus or minus D, then that is of this form, which we have denoted P with subscripts little d and capital D. Where in here, little d is the degree, and this capital D is where what gives us the critical points. So if we have any bicritical polynomial of degree greater than or equal to 3, with 2 critical points that are distinct and do not lie in our base field, then that polynomial will be conjugate to a map of the form A times P plus C, and this will maintain the field of definition. So this will stay in that base field. And here again, D is just a square-free integer. So now we have a nice form that we can look at to find all PCF polynomials with these irrational critical points. So what we get here is that if we have a cubic bicritical PCF polynomial that is not conjugate to a polynomial with rational critical points, then it's conjugate to a polynomial of the form a times z cubed over 3 minus dz plus c, where the triple DAC is contained in this set of 2 triples. So, putting all of this together, we obtain these 15 PCF polynomials with coefficients in Q. And this describes all of the conjugacy classes of cubic PCF polynomials with coefficients in Q. So thank you for listening, and the details will be presented on July 1st. Thank you.